All right. Well, those are good. Thank you. And thanks for coming back, getting into the afternoon here. So we're going to try and keep it fresh and interesting and relevant for you. So yesterday, for those of you that were here, we started to kick off this topic. This is our second year in CropX with this very unique device. There's nobody else in the industry that has a system like this and has the same measurement principle. As a result, the agronomic case studies with actual ET measurement on real agricultural fields are insanely rare up until now. So I think this is pretty exciting because you're going to see some graphs today from Avi. Nobody, even in the scientific community, my buddies in the university, nobody's got this kind of data before. So we're going to be working hard on getting these graphs out there, explained, recognized. But you heard it here first. So we're going to go into the science a little bit, and then time permitting towards the end, we can talk more about the applications. I know there were some questions and discussions yesterday about, okay, I think I understand this new device, but how do I use it commercially? So we'll try to get to some of that as well. But with that, let me hand it over to Avi.
Thanks, John. You guys can hear me okay? Excellent. I guess I don't need that one. You could take it. Okay. So I'm just going to run through a little quick intro like we did yesterday about ET. I will focus a little bit less on that. Just for those of you that didn't see it yesterday or want a refresher. So as we were saying before, ET, right, is a combination of two different processes, one of them being physical and one of them being biological. Evaporation, right, is when liquid water turns into vapor. It could happen on the surface, open water bodies, on the surface of leaves, and whereas transpiration, the biological portion, that's happening through the stomata that we see. So this is an image of stomates on the stomata underneath the leaf surface, and every time they open and close, depending on water availability, right? The trigger pressure. When there's a lot of water, they actually open up, and then when they get too dry, the leaves get too dry, they actually close themselves automatically. So actually, this is the fastest. This is relative to everything, the movement of water in the rest of the plant. This is a really fast process. And the purpose of that, why is the plant even performing transpiration, is because every time water leaves through these stomata, carbon dioxide comes in through those stomata too. And then that is why the plant turns, with photosynthesis, turns that CO2 into glucose and then eventually into everything that we eat. Yeah. When you say, I'm not sure. Do nutrients come through stomata? I don't think so. I think it's.
Yeah, so that's the kind of the concept behind foliar applications. That would be the mechanism of uptake into the leaves. I also believe that there's some adsorption through just the leaf surface itself and not the stomata, is my understanding, but I'm not a pro in that area.
Yeah, because typically stomata are on the undersides of the leaves. It can be on the top sometimes, very rarely, but yeah, essentially. And there was another thing I wanted to say about stomata, but it doesn't matter.
Also, I forgot to repeat the question. Just for the people on the Huba, I'll try to repeat everybody's question if it's not on the mic. Are the stomata just for gas exchanges, or do they do like solid or liquid nutrients as well?
Also, okay, I just remember now. Fun fact, the entire time the water is in the plant, it's actually still within a liquid phase. It only turns into a gas the second it leaves stomata. There's implications for that, but it doesn't matter for now. So how do we measure ET, right? Like ET is notoriously, it could be a difficult thing to measure by itself. Oftentimes we use the water balance method for making irrigation recommendations and things like that. So we'll use things like soil moisture probes and rain gauges and things like that to understand sort of what our water balance is. But as I said yesterday too, is that we can use an energy balance also, right? And so if we're using the thermocouple, as well as other, supplementary data like satellite imagery, and actually I prepared a little slide that will show how that satellite imagery sort of looks. It's not Sentinel, it's not Landsat, it's something else. And it's called geostationary satellites. And so we use that to construct the same sort of thing, but instead of looking at, it's an indirect way of looking at the amount of water we have in our field, as opposed to the more direct way we use with a water balance. So, and as I said before, it's a balance, right? We're trying to figure out, whatever comes in necessarily has to come out. So we have a certain amount of net radiation, right? Solar radiation, solar energy comes in, hits our field, and then has to be expressed out in some way or another. So some of it will go into the ground, right? That's the G component in that graph. So the net radiation is the yellow arrow coming in. And then the ground heat flux, that's some portion, a very small portion of it will actually go into the ground. That's that brown arrow going into the soil itself. Then I'm going to use this thing. Yeah, perfect. So then sensible heat flux, that's the energy that goes into actually heating up the atmosphere or heating up the air around us. And that's what you feel. That's why it's called sensible heat flux, right? And that's represented by that H arrow, that red H arrow on that diagram. And then lastly, the last way the energy can get expressed out is what we call a latent heat flux, or that's the energy, and that's represented by that. Let me see if I can get this right. Oops. That's represented by that blue arrow right there. Okay, so the good news is that some of that the energy that goes into the ground, albeit it's pretty not so significant, it does actually cancel out to zero on a daily basis. So it's something that we can sort of ignore in that calculation. And then if we rearrange the equation, just using some simple algebra, then we can actually get what we're interested in, which is our latent heat flux. So that's what we call the evapotranspiration, is actually just equal to the amount of energy that's coming in minus the energy that goes into the heating the air itself. So whatever's left over necessarily has to go into turning liquid into vapor. And the way we model these two things to calculate this is we use geostationary satellites because, I like to think of the solar system like a clock, right? Because it really is just like a clock. It functions fairly similarly. And you can actually figure out how much sunlight any given point in the Earth will receive throughout the day, at a specific point of the day even, right? The only thing, though, that will change that, and from day to day, it doesn't change vastly. But what does change every single day is the amount of cloud cover you have. And that's going to actually change the amount of energy that the system is receiving. So if we can model that using geostationary satellites, if we can model the amount of energy the Earth theoretically should receive, or a point, or a field should receive, and then we say, okay, but I know that there's 70% cloud cover, and then we could sort of adjust that to make sure that we're getting the balance right. And then if we have a thermocouple like this, then we can use high resolution temperature measurements to calculate the amount of energy that's going into heating the air, as well as all the turbulent fluxes that are going, eddies that are mixing the air and causing more causing the air to heat up as well. And then, so this is just like a little diagram.
Avi, if I could add here, maybe
Yeah,
just
please.
just a couple points that I jotted down from the conversation yesterday. There were a couple questions about the role of satellite and stuff. It also ties back to when Taha was talking about the new weather station, our approach of leaving off that radiometer. It is a expensive device, and we could also choose to use a radiometer locally on this station, this ET station as well in the field, and get rid of that satellite data feed. But from the data perspective, we've studied this extensively, and we really have found that you don't need that radiometer. Like these geostationary satellites, they're good enough. It's not like Sentinel where it comes like twice a week, and then you've got to do a lot of math and assumptions about what it would measure every other day. Mm-hmm. It sits there above North America in our case every single day and takes a good, accurate, high res measurement. And for all of our purposes, it's just as good as a radiometer. And that takes off hundreds of dollars of expense from this system. So that's the role of the satellite data, and that's why we don't use a radiometer. If someone wanted to get really crazy for a research project with this and replace it with a radiometer, we can talk, no big deal. But this is a very, I think, logical and sensible cost efficiency for us.
Absolutely. And I'm actually doing that right now.
Yeah.
That experiment right
Okay.
now. And that's really the same thing,
Yeah.
essentially. It's getting the same data. So
Yep. All right.
yeah. No, it's really cool. And like you said, we're getting an image every 10 minutes of the entire Earth. And actually, I have this cool little slide. This is actually this is the geostationary feed over North America during the eclipse just recently in April. And so let me see if I could play it.
I was right there in that path, just west of Little Rock and
Oh, yeah.
Mina. Yeah.
So this is what it looks like. This is what we're looking at. So when you see all the clouds above it, right? So those are actually is changing the amount of energy, the amount of solar radiation these parcels of land are receiving at any given time. There's also a fun fact, actually, is that like, how everyone talks about during an eclipse, the birds and stuff, everyone goes to sleep. Well, believe it or not, stomata close. They're like, oh, it's nighttime. Time to go to sleep. They like, it shuts down everything. It's just kind of amazing. It just goes to show you the role of like the sun in stomata is that it's a big deal for these stomata. It's the main driver of evapotranspiration actually is the sun. So there's the sun and then there's wind mixing too.
Even my kids got sleepy.
Yeah.
Yeah.
Every time I miss it, it's not fair. That's interesting. It's really funny. Okay, so now we're going to get into like the meat of it because you guys wanted to look at graphs, I think. We were looking at one graph yesterday, so I said, okay, I should add a bunch more graphs to this one because I think everyone's sort of interested. So in this graph right here, what we're looking at, there's a lot of things going on, okay? But the graph yesterday, I showed you guys, that was sort of a comparison of the KC that we derived from the sensor versus what we would see from like remote sensing, let's say. And one of the first things I did when I was really diving deep into looking into these case studies was to sort of understand, well, everyone I know is going to ask me, how does this compare to soil moisture? And this is like, so I went right to this, and I feel like I saw a lot of really, really interesting things that I would not have seen just with a soil moisture sensor alone. So in this graph right here, we have the blue line, which is that's the evapotranspiration from the sensor itself. And the orange line, that's the evapotranspiration that you would get from reference ET, so from a weather station or something like that. And these blue lines in the back, these blue bars, these are precipitation events, okay? And lastly, the black line, that's the profile sum in that field, okay? And so, so this is a cornfield. And what we see here is that during that critical time of July,
It's I know it's hard to read the numbers on the x-axis.
Oh yeah. It's
So
clear over here, but not over there.
yeah, so just like on the left-hand side, it looks like it starts at about June 1
Yes.
last year,
Mhm.
and then it goes all the way through to October.
Yeah, from
Okay.
June to October.
There we
Yeah,
go.
it's hard to see actually, really. So, and then this axis over here, this y-axis at the left, that's your daily ET in inches. And then there's also precipitation is in inches is also the blue bars correspond to this first one on the right. And then lastly, the profile sum corresponds to this secondary y-axis on the right too. So that's also in inches too. Well, I mean, it's kind of hard to see. There's a lot going on, but I want you to sort of like focus in on like there's the beginning of the season, there's the middle start of the season, and then there's the end of the season. Okay. And then in the middle of the season, like you see these red dots that I've highlighted over here. These are all days where the ET that we captured from the sensor was significantly greater than that from the reference ET. So if you were to be irrigating according to reference ET, and in that critical time period of July, if you were just to follow reference ET, you'd be under irrigating significantly. And actually for this field specifically, the difference was in that time period of July, that critical period, the difference was 0.75 inches. Okay, and that's around like 14% difference in the amount of evapotranspiration, and that's, in terms of actionable insights, you would be under irrigating your crop when it nearly needed it, because if it can evapotranspire, then it needs that. Also, what's really cool about this graph too is that you could see that, as time goes on, that the ET starts to really peter out, whereas the ET from the sensor peters out. But the ET from the reference ET, obviously, it doesn't understand, right? It thinks it's assuming that it's a grass, right? A well-watered grass surface, and it stays relatively high or much higher than it should. And actually, it's hard to see with this graph a little bit because of the proportions, but oftentimes whenever there was a wetting event or some sort of rain, I'm getting too close to something, I guess. Every time there would be a wetting event and the soil moisture would spike, you would see not the day of because it was cloudy, oftentimes, but the corresponding day afterwards, the ET would spike. And most of it was probably true to transpiration, and things like that. But at the same time, probably some of it was because of evaporation. So, and I think that I'm trying to see it here, but yeah, oftentimes that the ET though from the reference ET was typically too high and unreasonable too in the end of the season, like I said. We can go on to the next one. Oh, yeah.
Yeah, I'll just repeat for folks online. So the orange line with the reference ET and the blue line with actual ET, they just don't match. They just straight up don't match. They're the reference ET is just wrong if you interpret that as actual ET, which you shouldn't. Like there's nothing wrong with this reference ET calculation, but what's the definition of reference ET? It's the amount of evapotranspiration you would get on a well-watered lawn that day. Is your cornfield a well-watered lawn? No. So a lot of growers do, for various kind of old historical reasons, confuse reference ET with corn water use. They're different. They're different.
Yeah. Like you said, it's ignoring the fact that it's the crop that it is, and it's ignoring the fact that there's different conditions, that it's not idealized conditions. The total growing season, if I haven't done the total growing season, I could do that and send that to you right afterwards. But in July, I did that for July mostly.
Yeah, we got a slide on that here in a little bit.
Yeah.
Question was, have we ever looked at the total difference over a season? We've got a slide on it here in a minute. The other thing that I wanted to point out, I think a little bit relative to what Jason was saying, and also it touches on a conversation we had yesterday. The idealized ET curves that you see in textbooks are really smooth. And when we first started showing these graphs to some agronomists in the season, they're like, well, that's really spiky. I did not expect it to look that spiky. But you know what? It's real. The spikes are real, and you want to see the spikes because what are the spikes? Well, one is they're weather dependent. You're going to have more ET on a hot sunny day than you are cloudy, all other things being equal. And that's not reflected in those idealized growth related curves. Also the availability of the soil water. So we had some really interesting conversations early season where, even in a pre-plant or an emergence type situation, we were showing that the field was losing water to ET and that there was like little or no vegetation. And the conversation was like, well, does that make sense? Is that biased? Is it even reading my field? And the answer was yes, because in this case, it was a wet spring type of a situation, standing water on the field, ample soil water on the field. And in that case, your evapotranspiration sensor is not reading transpiration from the plant. It's reading bare ground evaporation.
Yeah, absolutely. And there's like an example I have. Oh, another question?
Question here is there an ET crop curve in use?
So we're about to ship that actually in the next couple of weeks. We will have that for the growing season. So yeah, that's the canopy graph that I spoke about last week. And I have one actually here prepared for us. So I can show that in a second. But
Sorry, Ben, can you read that one more time? Just make sure we're answering the right question.
The question is there an ET crop curve in use?
So they might be
Oh, I was
asking,
thinking-
is it embedded in this calculation? Like, is this calculation dependent upon a crop
Oh,
coefficient?
No.
The answer, I don't know what they're asking, but if they're asking, does this require a crop coefficient to get calculated? The answer is no. We're totally bypassing, like, we're totally ignoring crop coefficients from the literature.
Yeah.
If they're asking, are we going to be able to see a time graph of crop coefficient calculated by CropX using this data in the app? That's what Avi was answering.
Yeah.
Indeed, we're gonna go ahead and add that to the platform for
Yes.
this summer.
Absolutely.
Okay.
Okay, we can keep going. We have more of these. So, similar sort of graph, looking at the moments where ET and reference ET and actual ET sort of deviate. And you can see that like it's fairly significant. Again, the same thing in July. There's a lot of days where the ET is actually much higher than that from the reference ET. And that's something you would expect, right? That's like the peak of the corn season for these guys. And they're pumping out water and they really need that. And, you know, if you were to make the irrigation decisions based on that, on the reference ET, again, you'd be under irrigating and then you'd be impacting your yield and you wouldn't, it would just be something. And also in the case of this one, you could see oftentimes when the soil moisture starts to dip, you would see that the actual ET starts to dip also as well. See that right here, actually, at the end of July. Let me do it in this one because it's easier. Yeah, right here, it would dip out down more these 2 days, these 3 days, actually. So oftentimes the reference evapotranspiration, you know, it doesn't sort of respond the way you would expect it to. For this guy, actually, this one actually was used, the reference ET, sorry, the actual ET was 0.82 more inches more, so around the different than reference ET. So there was about a 16.5% difference in the amount of water usage from reference ET, or between the actual ET and reference ET. And this is also corn. So this is sort of what we were talking about before with a crop curve, a crop coefficient curve. So this is sort of like the same sort of thing as before, where we take the actual ET and then we divide it by the reference evapotranspiration. So the blue line is not the ET in this graph. It's actually the KC, so the crop coefficient, and the green line is the crop coefficient if we were to take it from remote sensing, okay? And you can see that oftentimes, you know, like there's a really pretty curve with the NDVI-based one, the remote sensing-based KC, but it doesn't take into account all of sort of the finer resolution, the days in between the satellite images themselves. And so, you know, there's a lot of examples here where you could see that in the middle of the season, you know, the soil moisture starts to get depleted and then ET collapses because it doesn't have anything to transpire itself. Also, talking about, you know, high evaporation rates in the beginning of the season, if you see, you know, in the beginning of the season, actually, there were a couple of days that were like the KC derived from the sensor was really high. And people were saying, what the heck is this? This doesn't make any sense. But the soil is like, as John's mentioned before, you know, it was a wet spring and there was a ton of soil moisture. And actually, this was a big conversation that we had. And I went back in to look at the literature. I said, this is crazy. And then, you know, that equation I showed before yesterday, Penman-Monteith, I found a paper from Penman, like 1955. He did a 16-year-long study looking at evaporation rates from bare soils. And when the soils are very wet and the water table is relatively high, soil KC values can even exceed 1.1.
Yeah, bare ground evaporation can really pump in certain situations.
Yeah, and so it's like, and that's something that people should know. Like we say that, oh, that's not relevant, but that is relevant because eventually, you know, your soil moisture is being depleted in one way or another. And there's no canopy actually protecting it either, if you think about it that way. So this is a really cool graph, and you could see actually that the soil moisture is like a huge player, and actually they move together. Oftentimes, when there's a wetting event, the soil moisture spikes, and then the ET will spike like the day after or something like that. And when the soil moisture starts to get low, so the ET also starts to get low too. So the ET sensor is like really seeing actually what's going on in your field. And it does it at a much more granular scale than you would see from remote sensing data, right? Because like we said, remote sensing data, you have an image maybe once every 5 days if you're lucky with no cloud cover.
We have a question. I have a question.
Sure.
If we know the actual ET, what is the value of knowing the KC, like its relationship to ETO? And if we say that ETO is not accurate anyways, ETA is the one that's accurate, what is the value of knowing KC?
So the ETO, it's not that the ETO is necessarily bad, right? It's a reference, right? It's something that you typically, well, the KC is, the way you calculate KC is looking at your evapotranspiration, whether it's from a crop coefficient over reference ET. But it's not that the ETO is the bad thing necessarily. If it's for grass, it's the perfect thing to do, right? But the value is that you're keeping track of your canopy. You're seeing the health and growth of your canopy. And you want to see that, with your growing corn, you want to see that your KC is getting above 1 or 1.1 or getting up to 1.2, hopefully. So it's a way of tracking the actual growth of your field. And on top of that, once you actually have reached your max canopy value, and then let's say you start going into fruit bearing for whatever crop, that's when you actually start to determine how stressed out your crop is actually too. Because you can use this at any deviation, any time that the KC goes away from what it should be from the curve, from max canopy, then it could be in stress. So that's one way of interpreting it. That's the value, I think. It's a means of normalizing its performance.
So it's a little, just to paraphrase it, like to me, tracking a crop coefficient graph, a calculated crop coefficient, not one from a lookup table, but one that we calculate dynamically, is a little bit like tracking NDVI, right? So it's like a proxy for overall canopy growth throughout the season. You can see senescence come in and see it go back down.
Yeah.
Thanks.
Yeah. It's like a crop phenology sort of thing. Here's another graph where we look at ET again. And you can see that, I'm just going to see, because I see it right here at the end of the season, we're overestimating evapotranspiration if we were to use the reference ET method. And also, again, the soil moisture and the ET are moving together a lot. It's a little bit messy here. Actually, it's kind of hard to see, but oftentimes they move up. Whenever one goes up, the other one will go up too. There are also a lot of cases here in the middle of the season, in July time period, when you want to make sure that you're getting your irrigation correct, that the reference ET was just way too low than it should have been. If you were to irrigate according to that. And for this guy, for instance, the difference between the two of them was around 16.5%, and the ETA was around 0.64 inches more. So that's there's a significant amount of water that you should be putting down. Also, the reference ET in the beginning of the season, because this sensor soil moisture actually wasn't that high in the beginning of the season, we see that the ET values themselves were not too high. And that, that the reference ET for a couple of days in the beginning were like very, very high, way too high, I think. And we don't see that same sort of case in with the actual ET. So, a lot of these examples are very similar, showing that during the critical time periods when people are making irrigation management decisions, that the reference ET is just not sufficient. Or if you're not growing grass, if you're growing corn, you want to make sure that you're getting your irrigation prescriptions correct, especially during this time. And here's another one. And a lot of these are the same sort of flavor, if you haven't noticed. But also this one too, super high rates of evapotranspiration from reference ET versus the ET, the actual ET from the beginning of the season. And in July, when it's most important, you know, the actual ET was much higher. And this one, 409. Yeah, this one, there was a difference around 5.575 inches, so a difference around 10% between the reference ET and actual ET, with actual ET being greater. And again, this is actually really pretty. You could see that the soil moisture and the ET's values are actually moving a lot together too. And that, you know, they both go down at the end of the season because things are cooling down, but the actual ET, you know, is showing that the crop is basically dead or gone, or it's senesced already. So whereas there's still an assumption here that the ET is high because, you know, there's ample water and it's grass, but we see here ET collapses because the soil is getting bone dry. I showed something very similar to, again, yesterday. This is also a similar graph with KC, and this is showing grass. And I asked this yesterday, and I'll say it again, but these times, you know, we see these like the green line is the NDVI remote sensing based KC, and the blue line is the KC from the sensor. And you could see, you know, there's for the cuttings, you could see whenever there's a cutting, right, ET collapses, and you see that in remote sensing based data, and as well as also in the sensor based data. But you get a much finer resolution. You get a daily value every single day. You get a value. Whereas with the remote sensing, you won't get that. And also the recovery period is much faster with the ET from the remote, the KC from the ET sensor itself. So it shows you that that the sensor is actually reflecting in-field conditions and it's responding much faster. Yes, question.
Question here is it possible to create and use a custom crop coefficient over time to affect water goals to purposely induce stress in the example of grapes?
Is there a way, custom crop coefficient, like a target canopy value? Yeah, so that was what they would do a lot in Thule, is that they would have targets for their max canopy, okay? Because with grapes, right, once you get to max canopy, any time that the grapes canopy or the ET values would deviate from that maximum, you know, efficiency, then we would be necessarily in stress. And people wanted to, you know, cause that stress, right? It was intentional, but not too much. So I don't think it's necessarily, you know, the KC is what it is, right? That's not something we can necessarily just change. It's not a parameter necessarily, because these things are being calculated and measured, not being put into the system. But we have means for putting targets for, you know, what your canopy value should be and what level of stress you should be in for grapes. Yes? Oh, wrapping up. Okay, yeah, wrapping up. Okay, sorry. I could talk about this forever. I'm sorry, guys. Okay, and so yesterday I showed the similar graph to this one with grass, but now I'm doing it the same one with alfalfa as I did yesterday. But I also want to show you guys sort of the difference between reference ET and ET during a cutting event. You can see that the assumption that the reference ET, everything is hunky-dory, right? It keeps going. But the ET collapses every single time that there is a cutting event. So this is something that's sure just reflecting, once again, it's just reflecting in-field conditions. Unfortunately, there wasn't a soil moisture sensor in this one, but I think it's like speaks for itself. So just to conclude, some takeaway points. The ETA was like much higher. It was around 14% greater during July for corn, right, than ETO. The ET sensor though showed really, really nice trends with remote sensing and soil moisture data. And it also, the ET didn't not only just trend with the other things, it actually preceded those other the remote sensing based data, and then also the soil moisture also in some cases too, because as I said before, stomata respond the fastest to stressors actually. So, anything you want to add?
How are we doing on time? Naomi, are we late?
Oh,
All right, we're done then.
okay. Any questions? Okay, thanks guys.
Thanks, y'all.